Everyone right now, go ahead, all draw your dots. It sounds like a rainstorm. It's really quite peaceful. Okay, maybe not so peaceful. Are you guys all caught up? Good heavens. Okay, that's enough dots. You're done with dots. That's okay. Okay, guys, we're going to go ahead and get started. As you were drawing those pictures, I hope that you all had this moment where you said to yourself, gosh, these are familiar, and somewhat in order to the ones that I drew in the homework. Guys, that is not obviously coincidence. This is a summary of everything that you need to know from the homework. If you know this, you know what you need to know for the test next week. But if there's any gaps, you've got to make up for them. Guys, that's why Mr. Miller and I do this way, because many of you could have written just about anything in your homework. These are the things you need to know. You ready? So guys, way back when, in the mid-1800s, a fine fellow came along and started studying gases. And he found out that when these gases bonded together, they bonded together in whole number ratios. He found that the atoms of one element were different than the atoms of another element. He found that these atoms were never created or destroyed. Sounds familiar? He and Antoine Lavoisier came up with the idea of the law of conservation of mass. Who on earth am I talking about? John Dalton. So John Dalton, through the study of gases, discovered some very fundamental things about the nature of atoms. So, and guys, you got to understand that back in these days, scientists were like pop musicians. They used to put on concerts, and people would come into their labs. Their labs had theater seating, and people would actually, for a Friday night date, get all dressed up and go into these labs and watch these scientists present what they were finding. And they would all, it's like being at the opera, they would all clap politely. It was quite lovely. So guys, they asked John Dalton, John, what does an atom look like? And you've got to understand John was British. So he had a different frame of reference than we do. So they said, John, what does an atom look like? And he said, well, it's hard and it's dense. And so I need something that's hard and dense. And so guys, if you all played pool, rack them up in the triangle break with the cue ball, 8-ball pool. Those are hard, dense balls, right? But in Europe, in England, they don't play pool. They call it billiards. So John Dalton said that atoms were like pool balls, like billiard balls, and this then is his model of the atom. You good? Questions on Dalton? Which comparison? Well, that he did. It was his idea that atoms are like billiard balls. It's just here in the U.S., we don't know what billiards are, or we call it pool. Okay, so then guys, when you don't need to know dates, but I don't remember, like 19, did any of you get a date for Thomson? 1902 or something, right? 09, so turn of the century, pre-World War I. So J.J. Thomson grabs this vacuum tube, and he hooks it up to a battery, and he passes a current through the tube. And what is electricity made of? Electrons. And he passes a current through the vacuum tube, and then he sticks a magnet next to the beam, which he can see making a screen glow. And when he stuck the magnet there, what happened to the beam? It bent. And what did that tell Thomson about that stream of particles? They had a charge. And he later called them electrons, and by using his cathode ray tube, he not only discovered the electron, but he showed that they were negatively charged because of the direction the beam bent in the magnetic field. Now, they went up to then Thomson and said, Thomson, what is an atom like? And he said, it's like pudding. It's like tapioca pudding. It's goop with a bunch of little balls in it. And those balls are the protons, or I'm sorry, the electrons, but then he figured if there was something negative, there had to be something positive. He didn't call it the proton. But guys, he said there's got to be negatives and there's got to be positives, like little balls of tapioca floating around in pudding. But again, because he's British, it wasn't tapioca, it was plum pudding. So he thought that an atom was like a sphere of goo with positive and negative balls like little plums floating around in pudding, plum pudding model. You good on Thomson? Okay, and notice guys, there's no P in Thomson. It's not Thompson, it's just Thomson. Okay, so then guys, along comes a guy named Robert Millikan. And here's the thing that's funny. Guys, look at the model that you drew for Thomson and look at the model you drew for Millikan. What do you notice? They're the same. Guys, Millikan does not have a model that he is given credit for, but guess what he did get instead? A Nobel Prize. That's a pretty good trade-off. And guys, you can actually go to the University of Chicago, walk into his lab, it's still set up, and you can see his oil drop experiment still sitting there just like it was in the 1910s when he was working on his Nobel Prize. So what did Millikan do? Well, he carried out a thing called the oil drop experiment. He took some oil drops, bombarded them with some radioactive particles, made them negatively charged, let them fall through a chamber. By repelling the oil drops with an electric field, he was actually able to quantify the charge on an electron. Thomson proved that it was negative. Millikan gave it a number. I forget the number. It's something in coulombs. But anyway, it was a big deal. Yeah. No, this is not a third model. Millikan does not have a model attributed to him. It's actually the same as Thomson's model. Okay, so then who came after Millikan? Well, then comes a guy named Lord Rutherford. Again, this was in England. It was in Europe, not in England, but it was in Europe. And so, guys, Rutherford's trying to peer into the inside of an atom. So what he does is he takes a piece of gold and he hammers it very, very flat like tinfoil, only it's made of gold. And then he shoots these radioactive particles at the gold. And what did most of the radioactive particles do? They didn't scatter, they went straight through. Why would they go straight through? Well, guys, if the nucleus is the size of a marble, how big is the atom? The size of Lavelle Edwards Stadium. And what is between the marble and the edge of Lavelle Edwards Stadium? Nothing. It's empty space. And so these alpha particles are flying through empty space like dropping balls into Lavelle Edwards Stadium. You either hit the very top seats or you hit the marble in the middle, or they fly straight through. But then every now and then, guys, and Michael said this a minute ago, what did every now and then one of those particles do? It bounced back. Now guys, think about it. If this is the nucleus of the atom, most of these particles are flying straight through. But what would have to be true if all of a sudden one of these particles bounces straight back? It hit something. And what has to be true? The thing that it hit, it's got to be stinking crazy dense, right? Because if this was just light and fluffy like a feather, it would just blast it through. This thing's got to be crazy dense. How dense is it? 6.2 billion cars inside this box, kind of dense, right? Pretty dense. And so Rutherford said, hey, whatever it is that's making these things bounce back has got to be crazy dense, and he called it the nucleus. So Rutherford, doing his gold foil experiment, proved that you had this hard, dense, and also positive. We'll talk more about how he knew it was positive later. Positive nucleus by shooting alpha particles at the gold. And guys, remember the word alpha particle. That's going to be important. So what did he do? he came up with what we call the nuclear model. He discovered the nucleus. Notice the electrons still look like the Thomson model. They're just pudding. They're just gloop. But now we've got a nucleus. You good? Groovy? All right. So now, guys, this. Some years later, and I don't know if you picked up on this, Rutherford and Bohr actually knew each other. So Rutherford, or Bohr, then follows up on Rutherford's work, and he said, hey, I want to take a look at the nucleus. Or I'm sorry, not the nucleus, the electrons. So he started studying the electrons, thinking that Thomson's model was wrong, and they weren't just pudding. And so what he did is he actually took these electrons and excited them with electricity, and as they moved around, they started producing light. And guys, by studying the light that these electrons were giving off, he learned that these electrons are not like pudding. They're not all just gooped in there. They're actually organized into orbits in the same way that the planets are organized around the sun. And we call that the planetary model of the atom. Now, atom, this is, sorry, atom. This is, Adam came up and asked me about the homework. This is why I put you off. You'll see in just a second. So guys, here's the problem. If you had come in here the very first day of class, and if instead of giving you my talk about how all of you are eventually going to need a favor and you want me to like you, do you remember that talk the very first day of class? Groundbreaking for some of you, I know. But guys, if we hadn't done that, and if I had just said, here's a piece of paper, draw me an atom, that'd be a weird way to start the day, right? But most of you would have drawn this, because most of you have this horrible misconception that this is what atoms look like. That the nucleus is just this ball of protons and neutrons, and the electrons. Some of you get really daring if you're really feeling good about yourselves. Some of you get a little wacky. Well, I can't draw it on here, but you draw the circles as like ellipses rather than circles, because that seems more scientific. So here, I'm going to need to write eventually. So some of you guys get really wild and crazy, and you do something like this. So you're here, and you're like, hey, what does an atom look like? And you do some of this, right? Because that's got to be better. Well, guys, you got to understand, this is all crazy, whacked out wrong. This is not what an atom looks like. The Bohr model of the atom is not correct. But here's what we're going to do. We are going to allow you to wallow in your ignorance until after fall break. We're going to let this be good enough. And Adam, this is what I was getting at. It takes about 2 weeks to break you of this horrible thought. So we're not even going to touch it right now. Guys, what we're going to do today is we are going to leave this alone, and we are going to focus on the nucleus. We're not even going to mess with the electrons. But after fall break, when it's electron messing time, this is where we're going to get you. And this is what is called the Schrödinger model of the atom. Now guys, Erwin Schrödinger was a funny guy. He was actually a slimy dude and a womanizer, but you'll learn more about that later. It's funny, every picture you ever see of him, he's got like this sweater with his collar turned up. He's a pop collar kind of guy. He had a lot of girlfriends. Anyway, he's really slimy, but really bright. And guys, the thing that made him unique is he was actually the first, if not one of the first physicists that did very little experimentation. Everything that he did was computational. He worked with math and developed mathematical models. And he created a whole new realm in science called wave mechanics. And his model of the atom is what we call the charge cloud model of the atom. Now, to help you understand how wacky this really is, guys, what do these little dots represent? What do these dots represent? It's the protons and neutrons are in the middle, and that's still true. What do the dots represent? Not electrons. It's one electron. That is one electron. simultaneously existing in multiple places and filling spaces as if they were large solids, even though they are actually point charges in space that have virtually no volume. Got it? Good. Guys, what I just said to you was basically the whole next unit. What I'm trying to communicate to you is that that model of the atom, and actually the pictures on the wall depict similar ideas. Guys, it takes a while. So again, we're going to leave you right here. We're going to let you think the electrons are like planets. We're not going to try to fix it. We're going to focus on the nucleus up until fall break, and then we'll fix the rest of it next unit. Good? Okay. Because guys, we've got, oh, wait for it, we've got a larger goose to cook. You guys ready to move on? Let's move on. Guys, we've got a whole nother problem to deal with. And here, I pray that some of you are embarrassed by this. Because guys, the nucleus of the atom is part of the 4th grade science core. I know that. I have a 4th grader. 4th grade science. They taught you about the nucleus of the atom. And you do want to write down this thing that says the problem of the nucleus. Guys, and you had science teachers getting up in front of you since 4th grade. Typically in elementary school, those teachers are timid because they don't like to teach science, which is understandable. They've got a lot of other things to do. But guys, right from the start, and please don't, this is going to be a bunch of pictures. Right from the start, guys, you've been seeing pictures like this. And there's the protons and the neutrons in the middle, and that's the nucleus. And around out here are the electrons. By the way, do any of you recognize the picture? Where is it from? It's from Scary Jumpsuit Guy. Right. And so, guys, we show you the nucleus, and then we start talking about all of these crazy things that are true about the nucleus. Like, for example, if we blow up the nucleus to the size of a stadium, how big is the nucleus? The size of a marble. So the nucleus is very, very small. And then we talk about the idea that if we wanted to stuff a 1-foot box, with enough matter to make it as dense as the nucleus, what would we have to put inside there? 6.2 billion cars. And we've got all of these really weird, really crazy ideas about the nucleus, but then when we write it down, we just do something like this. And you want to do this too, by the way. And guys, make this thing about 3 inches across. See guys, this is the way we as science teachers teach you the nucleus. We draw a circle in the middle, and because it's in the middle, you all go, oh, it's the nucleus. And then you're learning that there are protons and neutrons in the nucleus, although you've known that since 4th grade. And then, guys, around the outside are the electrons, and we've just been drawing them in one big circle, because that looks even more wrong than the orbits that you would like to put them in, so let's just call it what it is. It's all broken. But guys, we've got a problem. This is the same problem that Rutherford ran into when he proposed in the early 1910s that the nucleus existed at all. Guys, what's in the nucleus? Protons and neutrons. What's the charge of a neutron? 0. What's the charge of a proton? Positive. Guys, if you understand, what you said is true. Protons are positive, neutrons are neutral. When I say I mean If you really understand what you are, this is potassium, it could be any nucleus. If you really understand what you're looking at, you should look at that and you should go, no stinking way does that exist. Why not? Why not? Why should the nucleus of an atom not exist? Why is it since 4th grade have you been taking on faith that these things exist when they shouldn't exist? What's wrong with that? Well, yeah, it should be the size of a marble if the big circle was the size of the LaVelle Edwards Stadium. But whether it's to scale or not, it shouldn't exist. Why not? Really? Okay, I'm over my sadness now. Let's talk. What's the charge of a neutron? Nothing. What's the charge of a proton? Positive. And when you get a bunch of positive things together, do they naturally go, hey, let's hang out together? What do? They repel each other because like charges repel. And guys, that nucleus should just blow apart. It's like taking two magnets. Where are my magnets? Oh, look, magnets. So guys, if you take a magnet and you put it North Pole to South Pole, what do? They attract. But what if you go North Pole to North Pole? What do? They repel and fly apart. And guys, just like North and South Poles repel, or I'm sorry, North and North Poles repel, protons, positives to positives, all stinking repel each other. And the nucleus should just blow apart. Why doesn't it? Yeah. It's not directly because of the neutrons. It's not the electrons, because what do the electrons do? They attract. It makes it even worse. They're pulling. Why doesn't the nucleus blow apart? Well, guys, the answer is this. In our universe, there are only 4 forces. Two of them you're really accustomed to. Gravity and magnetism. Those are 2 forces. Magnets stick together and they fall because of gravity. But guys, there's 2 forces that you have never experienced, and one of them is the reason the nucleus sticks together. It is what is called the strong nuclear force, and it is the force. Did you notice did you like that? Let me do it again for you. I know, come on, one more time. Here we go. Here it comes, wait. Pulling it together, huh? Yeah? Okay, it's called the strong nuclear force. And guys, it is the force of attraction that holds the nucleus together against the repulsion of the protons. Guys, it's like a special kind of gravity that holds nuclei together. And it is called the strong nuclear force. Now, what does it mean to be strong? Guys, we are talking ridiculously strong. Like strong on an order that you have no bloody stinking idea. Crazy, wacky, stupid strong. So guys, how strong is it? Well, you ready for this? Are you guys done writing? It's amazing to me how much time I spend just babbling, trying to kill time while you guys are writing. Okay, so guys, here's the idea. Paper clips, right? What's the mass of a paper clip? About 1 gram. So here we've got 2 grams. Now guys, if we could take all of the atoms inside these 2 paper clips, and if we could take their nuclei, and what holds their nuclei together? Strong nuclear force. And if we could break the strong nuclear force in this many atoms, guess how much energy we would get? Enough to level the city of Hiroshima, which is about the size of Salt Lake. We did that. Yeah, we, literally, us, Americans, did that. Guys, when they dropped the bomb on Hiroshima, they had a chunk of uranium inside that bomb about the size of a volleyball. But they went back and did the math, looking at the blast patterns. They went back and did the calculations. And they think that of the uranium that was in that bomb, only a couple grams of it actually detonated. Only a couple grams of that uranium actually broke the strong nuclear force and let off that energy. And guys, that was enough energy to level Salt Lake, to level Hiroshima. So when we say that this pretty stupid blue star is strong, we're talking about strong on a level that we can't even wrap our heads around. It's called the strong nuclear force, and it overcomes the repulsion of the protons in the nucleus. Get the idea? Do you feel like your life is now fulfilled because since 4th grade you didn't even know what you didn't know that you should have known that you didn't know? Yeah.
Do they have an idea of what would happen if they did that to just one single atom?
Yeah. I mean, you could do the math easily, and it wouldn't be much energy. I mean, you might see a little flash, but it wouldn't be much energy at all. Yeah, Tristan.
I was thinking about like heat up the inside of one of those train cars, and if you like close the door, then like the air pressure.
Yeah.
Kind of like that stream.
Oh heavens, no. Yeah, no. What you're talking about is air pressure, and that is really cool. But you're not even close. I mean, imagine it's when they measure these amounts of energy, they measure it in kilotons of TNT. So kilo is 1,000. So we measure it in thousands of tons of dynamite. And we're actually now creating nuclear bombs that they measure in megatons. Millions of tons of dynamite. A 1 megaton bomb is easy peasy. We've got thousands of them. Imagine 1 million tons of dynamite all going off at once. Yeah, this is energies like you can't imagine. Yeah.
So, add a bomb goes off
Well, sometimes, and that's what we're going to talk about first. The ones that we dropped on Hiroshima and Nagasaki, yes, they were So Hiroshima was uranium, Nagasaki was plutonium, and both of those were fission bombs. They broke the atoms apart. Shortly thereafter, we created fusion bombs, and fusion bombs are not breaking them apart. They're putting them together, like the fusion that takes place in the sun, and that's when we started getting into the megatons of energy. They're crazy. So guys, strong nuclear force, you good? Okay, so guys, do not write this down. So here's what we're going to talk about today. This is an overview. We are going to talk about what happens when this strong nuclear force gets messed with. And guys, it can get messed with in one of two ways. Again, don't write this down. It can get messed with in high energy ways. These are fission and fusion processes. We'll talk more in a minute. But guys, they can also get messed with in lower energy ways that we call radioactivity. And guys, there's about a dozen different types of radioactivity. You just need to know alpha, beta, and gamma. So this is going to be our checklist for the day. We're going to talk about fission and fusion, which are both what we call high order processes. And then we're going to talk about radioactive decay, which is what we call a low order process. And those things are going on all around us right now, and we call it radioactivity. So we got 5 things. 1, 2, 3, 4, 5. You ready to go? Okay, you want to start writing this down. So guys, high order stuff. First of all, fission. This is not Utah speak for fishing. What'd you do this weekend? I went vision. This is fission. Now I can't even say it. It's that. F-I-S-S-I-O-N. Fission. Guys, this is the splitting of atomic nuclei into 2, I didn't want to write out approximately equal parts. Now guys, when this happens, what goes on is big atoms get smaller. You've heard of fusion, where small atoms get bigger. That's what's going on in stars. This is making big atoms smaller. So where do we do this? Where do we see big atoms getting smaller? Bombs, right? Nuclear weapons. But guys, also nuclear power plants. The same atomic chain reactions that we use to destroy those cities and end World War II. Guys, those are the same reactions that are going on inside nuclear power plants all around the world right now. Guys, 80% of France's power comes from nuclear power plants. And it happens day in and day out just fine until you have a tsunami that sends a tidal wave into Fukushima, and the next thing you know, the whole thing gets flooded, the backup power generators go out, and you've got trouble. You guys know about Fukushima, right? Maybe you know about 3 Mile Island. It's a nuclear power plant about 100 miles from New York City and Washington, D.C., in the middle of a river in Pennsylvania that almost blew up. And you've certainly heard of Chernobyl, right? No? Chernobyl was a nuclear power plant up almost in, what's the north part of Russia called? Siberia. And it just about blew up as well. But guys, the thing you've got to understand is that the same reactions that we use as nuclear weapons, we can harness and make peaceful use of by generating electricity. But did you guys know they're thinking about building a nuclear power plant in Utah? Do you know where? Green River. Yeah, right on I-70, right where the Green River crosses I-70 in the town of Green River. There's actually now, they're drawing up a proposal to build a nuclear power plant there. Is that a good idea? We'll talk more about it later. But guys, what is going on inside these plants? Well guys, this is it. Don't try to draw this, but let me explain to you what's going on. This is also what happened in Hiroshima. This is not what happened at Nagasaki. Nagasaki was plutonium-based. And I know this is hard to read, but guys, this is a uranium atom. This thing over here is a neutron. And what they do inside a nuclear power plant is they bombard uranium with neutrons. And guys, these neutrons act like wedges. They hit the uranium atom, and the uranium atom splits. And when it splits, it becomes two approximately equal smaller atoms, in this case krypton and barium. Now guys, in order for that nuclei to split, what has to be broken? The strong nuclear force. And when the strong nuclear force breaks, it releases energy. But guys, look, that's not all it releases. What are these three circles right here? Neutrons. And what do those three neutrons do? They hit more uraniums, and if they all hit a uranium atom, in the next generation we have 9 neutrons, and in the next generation we have 27 neutrons, and it keeps going up by multiples of 3, and the next thing you know, because of this exponential growth, you end up with a chain reaction and an explosion, because every time this splits, it also releases energy. Guys, this energy is the energy that leveled those cities and the energy that we use to boil water, spin turbines, and generate electricity. Yeah?
So when you're saying like all this is happening, is this happens really fast?
You know what? It's really cool. We can slow it down. Inside a nuclear reactor, what we do is, and you'll see video of this on Wednesday, the nuclear reactor actually looks like a swimming pool. And down in the very bottom of it is actually what they call the reactor core. And so, Kyle, think through this with me. What is it that makes this thing go fast and become a chain reaction? What is they? No. What are they throwing? The neutrons. So what we do in a nuclear reactor is we put, they're called control rods. They stand about, what is that, 4 or 5 feet, 4 feet tall? They're about that big around, and they're made of clay, the ceramic, not the same stuff you use down in weights class, but they're made of clay, and this clay absorbs neutrons. So what they do to slow this reaction down is they introduce these control rods, and the control rods soak up neutrons, and every neutron that gets soaked up is a neutron that didn't go to break a uranium atom, and they can slow the reaction down that way. That's actually what happened in Chernobyl. It became so hot in there that the control rods started to melt, and without the control rods, your nuclear reactor becomes a nuclear bomb. And so that's what they do, is they slow it down with control rods. Yeah.
So why the
It's interesting, because so here, let's answer that by looking at this picture. So Jared's question was, why in Hiroshima did not all of the uranium get consumed? So every time each nuclei breaks, it blows apart, there's a little explosion, and it gives off energy. When it does that, it pushes all the rest of the uranium atoms out. So the density of that core is becoming less and less and less. And as that happens, the likelihood that one of these neutrons will actually run into a uranium nuclei is always going down, because the core is always spreading out. And it was spreading out so quickly that only that very small percentage of the uranium atoms actually got hit by a neutron and flew apart. But it was still enough to release enough energy to level Hiroshima. So, yeah. Do you get the idea? You okay? So guys, let me show this to you maybe in a little bit different fashion. This is what it looks like if we put it into motion.
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amounts of energy in the form of heat, light, and ionizing radiation, an atomic explosion.
You get the idea? Go ahead. Say that again. No, it depends. When plutonium, I don't remember the numbers, but like when plutonium fissions, it's not 3. I don't remember how many it is, but it's only necessarily 3 for uranium. What was that? 238, 237. Yeah, it's only for that particular isotope of 235 where you get those 3 neutrons. It could be more or less. Yeah. Yeah, I'm going to actually, Adam, that's a good, how do they start the process? Many times it's with, like in our bombs, it's dynamite. And you're going to see in the video that we'll watch after the test, we're going to watch a video about how they built the Hiroshima and Nagasaki bombs, and we'll stop and talk about it then. But basically what they did is they pointed a bunch of dynamite, basically a bunch of rockets in. They stuck the core in the middle, put a bunch of rockets looking in, and had them detonate all simultaneously. And when they did, it just accelerated enough neutrons that it started. Yeah, it was crazy. So, you guys okay on fission? Okay, so now let's talk about this. Guys, the other type of high order process is called fusion. Guys, fusion is the nuclear reaction in which small atoms, they fuse together and they form larger ones. But you've already been exposed to this because this is what is going on in our sun and other stars. So let's see if we can make the connection. So, where did all the hydrogen come from in the universe? Big Bang. Then that hydrogen came together and what did it form? Oh, you guys are still writing. Good night. You guys done? How about now? Okay. So guys, then the hydrogen from the Big Bang starts to clump together and it forms stars. What's going on inside those stars? Hydrogen is fusing together and what is it turning into? Helium. It looks like this. One hydrogen atom and another hydrogen atom. This one happens to have 2 neutrons. This one has 1. They fuse together. They turn into helium. Again, that's a disruption of the strong nuclear force. It releases energy. That's the sun. So what happens then when all the hydrogen in the sun is turned into helium? Then what's it do? Starts to fuse helium together, making heavier and heavier elements up until which one? Iron. Once it hits iron, it can no longer fuse iron with other iron atoms. At that point, the star dies, and then what does it do? Supernova. It explodes. It releases a pantload of energy. That energy then starts to fuse the iron atoms together, creating all the heavier elements up to which one? Uranium. Yep, you got the idea? And those are what are called fusion processes. Good? Okay. So guys, that's half the conversation. Because there's a whole nother lower order way that the nuclei of atoms can break apart. Fission, they blast in half. It's a big deal. But guys, they leak. And they leak all the time. And we call this leak decay. Decay simply means to break down. And guys, understand this still involves the strong nuclear force being disrupted, just not in as large a way. So how do we know this happens? Because of this. Guys, this is what is called a Geiger counter. There's a tube in the back of this Geiger counter that has a gas inside of it, and every time a radioactive particle goes through this tube, it creates a little current that a detector picks up, and then it makes a beep. You'll notice that this is beeping. Not very fast, but it's beeping. What does that mean? Well, guys, it means that there's radiation all around us. It comes from the stars, it comes from the lights, it comes from radioactive elements that are all around us. And guys, it's called background radiation. Our bodies are being bombarded by radiation all the time. A lot of it gets absorbed in the atmosphere. So guys, this is kind of interesting. If you take a plane flight from New York to Los Angeles, you're 40,000 feet in the air, right? Less atmosphere. You actually absorb a year's worth of radiation flying from New York to LA. Isn't that crazy? Because if you were to take this thing up in the plane with you, it'd be beeping a lot faster. You absorb a lot more radiation. But then don't you think that airline pilots should have a higher rate of cancer because they're soaking up all this radiation flying all over the world? It doesn't happen. So guys, understand that even though we are exposed to radiation, that little bit of radiation is no big deal. But there's other sources of radiation, like this chunk of uranium, that are a big deal. Guys, this thing is leaking radioactivity and dirt like stinking crazy. This is what uranium looks like when it comes out of the ground. This is what's called uranium ore. The yellow is the uranium, and then the rest is just the dirt that it's trapped in. But guys, right now, if you could see radioactivity, you would see this thing just going shooting particles all throughout the room. And you can see that it happens so quickly that this thing can't even keep up, right? Crazy radioactive. So guys, let's talk about what's going on inside these uranium atoms. Well, there's actually 3 types of radiation that you need to know about. You need to write these down. The first one is what is called alpha decay. Guys, alpha is abbreviated this. That's the lowercase Greek letter alpha. But guys, we don't write alpha particles like that. This is what we're going to do. We're going to go helium 4/2. That is what an alpha particle is. It's a helium nucleus. Now, with the understanding that you all just took the last test, you'd better get this right, or I'm going to force you all to go back and retake it. Guys, protons and neutrons in the nucleus. What does the bottom number tell you? The number of what? Protons. There's 2. What does the top number tell you? You better, protons and neutrons. So how many neutrons are in this if its mass is 4? 2. 4 minus 2 is 2. So guys, that is an alpha particle. An alpha particle is a package of 2 protons and 2 neutrons, which is the same thing as a helium nucleus. Doesn't have any electrons, so it's an ion, but that is an alpha particle. It is 2 protons and 2 neutrons. It's really just a helium nucleus. Now guys, here's the other thing you need to know about alpha particles. They are big, and they are fat, and they are slow. Sounds like a bad introduction to a joke. How fat and slow are they? They are so fat and slow that Ernest Rutherford shot them at gold foil, thinking if alpha particles could get through, anything could get through, because they're so big and so fat and so slow. Did y'all pick up on that gold foil experiment? The radioactive particles he shot were alpha particles. That's why he picked them, because they were so big and so fat and so slow, he figured if they could get through, anything could get through. Okay? So guys, what's going on then? Well, here's the idea. Squint and find the uranium atom inside this rock. Y'all found one?
Oh, I got
You got it right there? Oh, it moved. No, it's gone. Oh, wait. Ah! You see what it just did? It just went through alpha decay. Yeah, that one that Parker was looking at, that one right there, you probably didn't see it, but he did. Guys, there was this one atom right there, this uranium atom, and it went through alpha decay. And what happened? Well, all of a sudden it went and it shot out a helium nucleus. What did it really shoot out? 2 protons and 2 neutrons. So all of a sudden that uranium atom that Parker was looking at all of a sudden went and it shot out 2 protons and 2 neutrons. But guys, what happened to that uranium atom when that happened? Is it still uranium? No, it lost 2 protons. So what is it now? It's not element 92 anymore. It is now element 90, which makes it thorium. So why did it happen? It just happens spontaneously. Guys, uranium is very unstable, and all of a sudden it's just hanging out and it just shoots out an alpha particle. The thing that you've got to know is what happens to the thing that's left over. You need an ROT. This is our first time doing an ROT. ROT is rule of thumb. And the rule of thumb is this. When an atom goes through alpha decay, Z goes down by 2, A goes down by 4. Write it down, and then I'll explain to you what it means. You okay? So guys, trust me on this. Don't try to write this down. Just trust me. You'll be fine. Just watch. Here's what you've got to be able to do. Instead of uranium, let's talk about radium. And it says, what happens to a radium-226 atom when it goes through alpha decay? Well, guys, how are we going to represent this? Well, when it goes through alpha decay, what comes out? Come on, what comes out? 2 protons and 2 neutrons. So what does that do? Well, here's how we represent it. So here we have radium with a mass of 226. Guys, what's this right here? What do we call this? Alpha particle. So the question is, when radium releases an alpha particle, what's left? Well, guys, watch the circles. How many protons are in radium? 88. How many neutrons are in radium? Subtract. It's 138 and 88 protons. Now, guys, what about this? What is an alpha particle? How many protons? 2. How many neutrons? 2. So it's 2 and 2. So then the question is, what's left? So if we start with 88 protons and we lose 2, how many are left? 86. So is this still radium? No, what is it? What's element 86? Radon. So this is now radon. But now, guys, watch this. If it started with 138 neutrons and it lost 2, how many are left? 136. So this does not weigh 226 anymore. It now weighs 222, 86 plus 136. So when this atom goes through alpha decay, it turns in to this. But guys, watch this. What is the top number, A or Z?
Z.
A. Look what happened to A. What did it do? Went down by 4. What happened to Z? Went down by 2. That is the rule of thumb. Huh? Do you like it? Okay, if you don't like it, get over it because you need to know it. You good? Okay, so now guys, watch this. Coming back to our chunk of uranium. Good night, right? Why is this thing beeping? It is beeping because these uranium atoms are shooting out alpha particles like crazy, crashing into the Geiger tube and making it beep. But now guys, watch this. Watch close. You ready? Why did it slow down? Because my hand is in the way. And so what must my hand be doing?
Shielding.
Shielding it, soaking up particles. But guys, listen, this is background. Pretty slow. This is crazy full on, and now this. Guys, what's going on is this. The alpha particles are so big and so fat and so slow, they can't get through my hand. They are not bouncing off my hand, they are lodging in my hand. But is anything making it through? Don't worry about that. Is anything making it through? And what must be true of the things that are getting through my hand? They're smaller and faster than alpha particles. Beta particles. Here we go. So guys, beta particles, which we write like this, are crazy. This is crazy. If you understand anything that you've learned in the last 3 weeks, this is crazy. So guys, take a peek. This is how we write a beta particle, that sexy B. But this is the way we're going to do it. What does the E mean? Electron. But guys, when we write an electron, don't we do it like this? Right? Charge in the upper right. Look at where the charge is. Lower left. And that is not a mistake. We write it like that to communicate that this is not an electron that was orbiting the nucleus. So what on earth is a beta particle? Well, guys, a beta particle is an electron. Sorry, that skipped. Let me come back. So, guys, a beta particle is an electron. But read what it says. It is an electron originating from the nucleus. What? Originating from the nucleus when a neutron becomes a proton. No. Yeah.
Does it release a neutrino?
No. I don't even know what that is. So guys, let me get this straight. So what you're telling me here is there are no electrons in the nucleus, right? The electrons, the nucleus is just protons and neutrons. The electrons are moving around the outside. So there's no electrons in the nucleus. And that's true, there aren't. But a neutron can magically become a proton, and when it does, it shoots an electron out of the nucleus. That is exactly what we're saying. Guys, neutrons can just amazingly turn into protons, and when they do, they shoot out an electron. But there are no electrons in the nucleus, and that's still true. So guys, that's what a beta particle is. It's an electron that comes out of the nucleus when a neutron becomes a proton. Now, you got to understand, these things are small, and they're very high energy. So what do these things do to the nucleus of an atom? Well, here's your rule of thumb. When an atom goes through beta decay, Z goes up by 1 and A stays the same. You okay? So guys, try this. Don't write it down, but just watch. So what happens to iodine 127 when it undergoes beta decay? And by the way, guys, this isotope of iodine, along with other isotopes, they add to our table salt. Have you ever looked on a thing of salt and it says iodized? They put iodine in our salt. It keeps us from getting some medical issues. So they give us iodine in our salt. And some of that iodine is actually iodine 127, which is radioactive. So if you held that Geiger counter up to a thing of table salt, it would start to click. Not really fast, but faster than background. It's radioactive. So what happens to that iodine in table salt? Well, guys, let's play the same game. So here's our iodine 127. What on earth is that? A beta particle. How do we know that it's a beta particle and not a normal electron? The negative 1 is down and to the left. So what does this look like? Well, guys, here is our iodine. 53 protons, 74 neutrons. Now, what is a beta particle? What is this? It's an electron coming from the nucleus, but it's an electron. Now, when this happens, guys, what happens to the nucleus when the electron is released? What happens to a neutron? Turns into a proton. So what happens to the number of neutrons? Goes down by 1 to 73. What happens to the number of protons? Goes up by 1 to 54. So is still iodine. No, it's element 54, which is xenon. But guys, when you add 73 and 54, what do they add up to? 127. Because protons and neutrons weigh the same, the mass doesn't change. So the mass didn't change. The atomic number went up by 1. Get it? There you go. So now, guys, let's play the same game one more time. You ready? Full exposure. Full exposure. Why is it now slower? Alpha's in my hand, it's going through. Beta. Can we stop the beta? What would it take to stop the beta? Something more dense than my hand. Lead. Come on. Okay. Here we go. Full on, right? Alpha in my hand, beta going through. Now watch. Hear it slow down? Yeah? Faster than background though, right? So everything, no alpha, no beta. But still faster than background. So what does that tell us? Something else is getting through. And guys, the stuff that is getting through, we call gamma radiation. Now guys, gamma is even crazier than beta. No, it's not. Do you like gamma, the little y character? That's the lowercase Greek letter gamma. And guys, it goes like this. Gamma radiation is actually not a particle at all. It's like light. It's just that we can't see it. It is. It's very high frequency light. It's actually the highest frequency light that we know of. And guys, because it's not a particle, it doesn't change the atomic number and it doesn't change the atomic mass. It's not a particle at all. It's just energy. But guys, here's the thing that's cool. It never happens on its own. It is just a relaxation process. So what happens is a nucleus goes through alpha decay. Out comes a helium nucleus. That causes stress. To reduce the stress, the nucleus will then go through gamma radiation and release the energy caused by the alpha decay. Same thing with beta decay. Beta decay causes stress. To release the energy, the stress, it goes through gamma decay, which releases the energy brought on by another radioactive process. So guys, there you have it. Alpha decay, beta decay, gamma decay. So here's the question. What do you have to be able to do with this? Well, guys, are you all caught up? Good? All right. So guys, don't write these down. But this is going to be in your homework, so let's talk about it. So, what you're going to do is you are going to identify the type of decay and then fill in the blanks. But, guys, this can only be alpha and beta decay. Gamma decay does not change the structure of the nucleus. So here's what you do. Take a look and compare. The atomic number goes up by 1. The atomic mass stays the same. What kind of decay is that? That's beta decay. So we'll write beta right here. And then guys, how do we represent a beta particle? E minus 1. Good? Okay, now watch this. The atomic number goes down by 2. What kind of decay is that? Alpha. Now, when something goes through alpha decay, how do we write an alpha particle? He 4 over 2. But guys, notice when something goes through alpha decay, the atomic number goes down by 2. What happens to the atomic mass? Down by 4. So this would become lead 205. Good? Okay. Now, what's this? That's an alpha. So this is alpha decay. So what goes in the space? Well, during alpha decay, what happens to the atomic number? Down by 2. That's 90. What happens to the atomic mass? Down by 4. That's 234. And this is no longer uranium. Element number 90 is thorium. Good? Okay. So guys, I've got your homework for you. We will grade it on Thursday or on Wednesday. And then remember, gang, on Wednesday, we're watching videos and you're writing papers. So plan on that for Wednesday. Then Friday will be the last of the new material for this unit. These are all B day, of course. The last of the new material for this unit. And then your test will be next week. Well, so the end of the term, as far as Skyward knows, is the 24th. The end of the term for us is next Wednesday. Guys, remember, if you are missing any late labs or homework for the current unit, that's all due next Wednesday by 2:15. Yeah, guys, test retakes are Tuesday, Wednesday, and Thursday. Tuesday is with me, Wednesday is with Miller, Thursday is with your teacher.